Mr. Wolfe here, and I'm going to be going over target 3, which is we're going to be continuing circular motion, so target 2, but we're also going to be combining in some target 1 to mathematically model circular motion. And so I want to bring up this question, our driving question of the unit. Why do astronauts in the space shuttle float when orbiting Earth? So by doing some calculations, we could better answer this question supported by evidence. But before we start target 3, let's do a little bit of a target 2 review. And let's just identify the centripetal force that keeps the shuttle from flying in a straight line in the direction of that force. So our space shuttle, we're going to say that our space shuttle is going to be right there in space. Space shuttle. And since it's going in circular motion, we know that the force has to act centripetally. Essentially, it has to be pointing towards the center of our circle. And specifically, this is going to be our force of gravity that's pulling that space shuttle towards the center of the Earth. And since we also know that acceleration is directly tied to force, acceleration is also going to be going centripetally as well. All right, finally, we're going to have that velocity, right, going to be tangent to our circle. So this is going to be for a space shuttle orbiting clockwise. All right, so let's start with some calculations. And first, let's look at some of the formulas we have. And a lot of them are going to be familiar. Like we've worked with Newton's second law equation before. We've dealt with target 1, our force of gravity equation here. We know our distance equals velocity versus time equation from our constant motion unit. I think it's important to write that this is for constant motion here. Now, the only difference is for distance, we're no longer traveling in a straight line. We're going to be going in a circle. So for distance, if we want to calculate that, we have to know the circumference of the path that an object's going to be taking. So really our only new equation that we're going to be dealing with is the centripetal acceleration equation. So to help us answer our driving question, we first need to calculate our force of gravity between the space shuttle and the Earth. And we already calculated that in class, and we got about 1.02 times 10 to the 6 newtons. Essentially, that's really close to 1 million newtons. Next, it asks, calculate the shuttle's centripetal acceleration. Essentially, what we're going to be looking for right here is we're going to be looking for AG, the acceleration due to gravity, at this point above the Earth. And so remember, in the context of our driving questions, most people said that at this point in space, that the astronauts float because that there's zero gravity. So if there is zero gravity right here, what would be the acceleration due to gravity that we would expect to calculate in this instance? So my unknown in this case is going to be my acceleration due to gravity. So these are the only two equations that I could use here. All right, and I don't know my velocity at this point, so I'm going to use my Newton's second law equation in this case. And my only force in this case is going to be the force of gravity, so that's going to be my net force. And so my net force is going to be 1.02 times 10 to the 6th. And that's going to be equal to the mass of my space shuttle, which is going to be right here, 115,900 kilograms. And then we're going to solve for acceleration. When we do the math on this, we're going to get that the acceleration is going to be equal to 8.8 meters per second per second. And if you're curious why it's not negative, or why I didn't make the force negative here, is because going down, but this is the force at any point when we're going around in the circle. So that direction is always going to be changing. So just to keep it simple, we're going to leave our force and our acceleration positive in this instance. So we got our acceleration to be 8.8 meters per second per second. And let's think about how that relates to our prediction of what we should get and how it relates to our question over here. And also keep in mind this 8.8 is not too far away from the 9.8 meters per second that a person experiences when they're on the surface of the Earth. So I'm curious, based on our calculations, based on our evidence, how would you guys go about answering this question now? So we're going to move on, but I did want to get your guys' opinion or thoughts in terms of what you thought this answer is as we continue to reference this throughout the unit. All right, so at this point, we really haven't done too much new. We've found the force, but we already know how to do that from other targets. We found the acceleration, but we also know how to do that from other targets. So really, the only new variables that we care about finding with this target is going to be our velocity and the period. essentially the time it takes to make one revolution. And so let's calculate our object's velocity. So we know we're looking for velocity. And so let's look at our equations over here. We could use our distance equals velocity versus time, but we don't know the time it takes for our space shuttle to orbit the Earth. So our only equation that we could really use is going to be our centripetal acceleration equation right here. Because we know our acceleration due to gravity, which is 8.8 meters per second. And we're going to also know the radius of our Earth plus the height that the space shuttle is above the Earth. So our radius is going to be both of those things combined. All right, so let's draw out our equation. AC is equal to B squared over R. So if you're curious, Mr. Wolfe, this says AC, this says AG, how can we plug this in here? So all this AC is saying is that this is a centripetal acceleration. Essentially, it's just saying this is an acceleration that points to the center of our circle. And in this case, our acceleration due to gravity, whether it's here or whether our acceleration is like our space shuttle here and it's pointing this way, it's also going to be pointing towards the center of our circle. So we could use this quantity here. So 8.8 meters per second, we don't need the units, is going to be equal to what we're looking for, our velocity, divided by our radius. And remember, this is still going to be the radius of essentially the path, the circular path our object's taking. So we have to do the radius of the Earth, which is going to be 6.378 times 10 to the 6th. We got that in our useful values up here, plus the height that the space shuttle is above the Earth, 354,000 meters. So let's take our calculator out for this. I would highly recommend that you guys just go through the calculations just to make sure you're getting the input stuff right. All right, so 8.8 times the radius of our circle, 6.38 second e to the 6th, which is our radius of the Earth, plus the height the space shuttle is above the Earth. And we're going to get this really big number. But keep in mind, all we found here when we multiplied these quantities is velocity squared. So we're going to need to square this value. And we're going to get our velocity to equal 7,696.9 meters per second. So we could look at this quantity and say, wow, this space shuttle is going really, really fast. But exactly how fast is 7,696.9 meters per second? Well, if you do the conversion on this ends up being 4.8 miles in just 1 second. So that is incredibly fast. So we found our space shuttle's velocity. So now the last thing we're going to be looking for is going to be the period, the time it takes for our object, in this case our space shuttle, to make one complete revolution. Essentially, how long does it take the space shuttle to orbit the Earth when it's going 4.8 miles per second? So calculate the period of the space shuttle around the Earth. Looking at our equations, the only equation with time is going to be distance is equal to velocity times time. So distance is equal to velocity times time. Remember that this is going to be our constant motion equation. And even though our velocity is changing, because the direction's changing, our space shuttle, or whatever our object is in circular motion, is still going to be going at a constant speed. So our distance here, remember, is going to be essentially the path of the circle. So we have to find the circumference of our circle, so 2 pi r. So we're going to put in 2 pi r for our distance, the circumference of our circle, and then solve for time. All right. So again, our radius is going to be what we have right here, the 6.378 times 10 to the 6th, the radius of the Earth, plus how high that space shuttle is above the Earth. And that's going to be equal to our velocity, what we just calculated over here, 7,696.9 meters per second. And then we're going to solve for time. All right, so let's enter this into our calculator. So I'm going to do 2 times second pi. You could also do 2 times 3.14 if you want. Multiplied by 6.378 second 1/6 plus, and then divided by our velocity. And we're going to get our time to be 5,495 seconds. And again, that's our period, the time it takes to make one revolution.
Right.
And so this time right here doesn't give us a whole lot of context. Like, what does this time? Like, what does 5,495 seconds mean? Well, if we do the conversion on this, that's going to be essentially going to be equal to 1.53 hours. So when you're going 4.8 miles per second, you're able to circle the Earth in less than 2 hours, in just an hour and a half, essentially. So these space shuttles are traveling extremely fast around the Earth. All right, so we just found the period time. So we've been able to find force, acceleration, velocity, and period. And remember, for target 3, it was really just these quantities that were new, essentially, in terms of like how to find them. And we used our equations up here. So that does it for target 3, but make sure that you answer the 2 practice questions that are going to be coming up.